Okay, good morning, everyone. It's 10 p.m. at night here in Singapore, but looks like most of the people are in the U.S. So very good morning to you. So today I'm going to talk about collaborative intelligence and a particular approach to it, and an integrative approach to collaborative intelligence. So we all know what collaboration means, and it's about working with someone to make something or to do something. And we also know collaboration is not an easy task, and it requires having a common goal, trusting each other, clarifying roles from the beginning, communicating effectively, and much more. But there are very clear benefits of collaboration. Right? So an artificial agent with collaborative capabilities that will be able to do a natural interaction with humans, and it can also make real-time adjustments and adaptations that is impossible in automation, for example. So in manufacturing domain, we might have these kind of collaborative intelligence scenario. So this is a very simple one where person is trying to assemble a gearbox. So the gearbox has some components that are quite heavy for the person to lift. So this user wants the robot to help out. So she might say, help me assemble this gearbox. And it would be nice if the robot can actually figure out that there are heavy parts involved, and if the robot knows that this person has limited capability of lifting objects. So it would be nice if the robot can say, sure, the output assembly is quite heavy, so I'll pick that up. And later on, they work together, and the robot knows how to coordinate in the physical space and say, let's put them down together so that we can insert this gear assemblies properly in the base case. So that's an example in the manufacturing domain that the project I'm involved in is using for demonstration purposes. So there are a few facets of collaborative intelligence. A collaborative agent will need to understand the situation, and it needs to know how to do things in this domain. It needs to know about itself and others involved in the task. It needs to understand these other people or agents' intention, and it needs to understand what they're saying, and it needs to be able to explain itself so that others can understand it. And additionally, it might also learn from others. So if you try to map these high-level aspects of collaborative intelligence to something more concrete, you might see these things: multimodal perception and inference to understand the situation, common sense and domain-specific skills to do things, and meta-level knowledge to know about itself, and some sort of theory of mind to model others, and capability to recognize intention and understand language and gesture, and also ability to generate language and gesture. And it might also learn from instructions or observations. Now, the question is how we go about putting these capabilities. So there are a couple of approaches to intelligence, and one of them is a fragmented approach, where you add new boxes, new black boxes when you need new functionalities. So for example, if you have a system with sensors and execution module, if you need some high-level decision-making, you might say, okay, I'm just gonna go ahead and add a planning module that's gonna talk to execution. And we might also add language understanding and generation modules or metacognition or intention recognition and so forth. So you can keep on adding these new functionalities as modules. But the problem with this approach is that these modules, they don't see what is happening in each other. So they communicate through some sort of interface that's defined, but that's about it. They don't have any idea what's happening inside. So these boxes are, these modules are black boxes shrouded in the mystery, I guess. So another approach to intelligence will be an integrative one, where we have this framework, a psychologically plausible framework, where we have long-term memories and short-term memories and low-level buffers that interact with the environment. And whenever we're trying to add new capability into the systems, we might add new processes within this framework that is using these components that already exist in the system. So often we call this framework cognitive architecture, and this is basically how we do our research in most cases. Of course, when we're doing research in cognitive architecture, we still often add components to it. And I believe that's because nobody has a complete framework that can model human cognition just yet. So when you're trying to add a new capability and your architecture is missing some component that supports it, then obviously you will have to add that component to it. But later on, if you have a fairly complete framework, fairly complete cognitive architecture, then you will end up adding processes that work over them. So I'll be taking this integrative approach to collaborative intelligence, and given my background in Icarus architecture, I will take that architecture as a starting point. So we have a system that receives sensory data from the environment in a perceptual buffer, and using that information and the long-term concepts in the conceptual memory, it performs the inference, and based on that, it figures out what kind of goal it needs to pursue at the top level through goal reasoning. And then it will go ahead and retrieve some skills that are relevant and instantiate them for the current goal, forming the intention. And the intention will lead to some sort of execution, and that will be done through the motor buffer onto the environment. And all the while, there is this episodic encoding that's happening to store the personal history of the agent in the episodic memory. So given this system, to enable it for collaborative behavior, we're going to add multimodal perception that uses the latest techniques for low-level visual classifiers, classification, and language parsing. And also, we'll add a new process that takes observed human behavior from episodic memory and matches procedures from skill memory for intention recognition. In addition, we're going to store common sense knowledge in long-term memories, existing long-term memories for concepts and skills, so that the system can use existing processes like inference, skill retrieval, and selection, and problem solving using the common sense knowledge. And finally, we're going to add some multimodal motors so that the system is able to do, say, generate dialogues. So as a result, we have this system. It's the extended architecture, but nonetheless, structurally looks very similar to the original architecture we started with, because we mainly added new processes rather than adding a new module that takes on the new capability. So this project on collaborative intelligence I'm involved with, it's a 5-year project, but it's fairly new. So we're only just past the year 1 mark of the project. So a lot of implementations are still in progress. So I'm going to talk about 2 examples of architectural implementation. So first example is intention recognition and plan understanding. And we have a new process that starts with an episodic memory that stores human actions as they unfold. Then an event segmentation process, it detects intention boundaries, and the system matches the new low-level intention to a long-term skill it has, and then record the recognized hierarchical intention in short-term goal intention memory. And this process assumes that there is grounded perception that recognizes low-level actions in the background. And also the short-term memory is able to store intentions for multiple agents. So as for the grounded perception, we have a system that can parse in real time multimodal inputs like vision and speech for now, and later on touch as well. And it will parse these inputs into task operations and human instructions that are recognized. And it will be able to relate these things onto the task representation you see on this slide, which is essentially the skill hierarchy that exists in the cognitive architecture. And the second example of architectural implementation that we're working on right now is about common sense-based instruction understanding. So we're developing a new process that starts with parsed utterance that appears in the perceptual buffer. And given this utterance, the system matches the verb in the utterance to a common sense skill frame or a domain-specific skill stored in the long-term skill memory. Then the system matches semantic roles against the skill frame, like take the subject in the sentence, the object, and the manner, and those kind of things. And it matches against the skill frame it found, and we code the matched intention in the short-term goal memory. And this process would assume, again, grounded perception and parsing the recognized instructions in the background. And also, it needs a common sense knowledge base for verb frames. So the system will have verb frames stored as actionless skills in long-term memory. So it's not going to be stored in a separate common sense memory or anything like that, but it will just be stored as skills in the existing long-term memory, but without any action items inside. So this is for linguistic understanding, so it doesn't really have to do anything onto the environment. So the system used these verb frames as templates for understanding instructions, and the matched frames are mapped onto the domain-specific grounded skills for execution. So in the end, if the system is to execute something in the world, then it needs to map whatever the user said onto the thing it can do in the domain. So going back to the manufacturing domain we use for evaluation, we're currently using a gearbox reworking procedure as our scenario for evaluation. And there are several use cases we can have our collaborative agent participate in the scenarios. And the first case is where a human teaches a robot for through a demonstration. So let me play this video, and if you, I guess this one doesn't have the sound, but for later videos, if you somehow don't hear the sound, then let me know.
Start populate casing base.
So in this video, we have two people working on a collaborative task to populate a gearbox. And you notice that these three components need to be
Populate the casing base complete
to get before they can get inserted into the casing base. And the system watches this as it happens, and it will basically form this task hierarchy, like task decompositions you see on the left, and figure out the procedure to do this. And then once it does that, then it will be able to replace one of the human and perform the collaborative task. And again, this particular video doesn't show the robot already doing it in the way I explained it. So this is you can consider this as a mock-up of what we're aiming for. And here's another use case where, again, the human is teaching a robot, but it's a little more complicated than the first one.
Load the casing base onto the pallet.
So now, we
Casing base found.
that the system is able to detect these different types of objects
Over the
already.
casing base.
And this person is explaining
Casing base
what needs
found.
to happen in sequence. So you notice on the left-hand side that the system
The
detects
output
objects
cover
involved
on
and
the
what
casing
needs to
base.
be done. And on the
Output
right-hand
hub
side,
cover
you
and casing
see
base found.
tracked operation, tracked task that
The small
goes on
hub
while it's
cover
happening,
on the
and
casing
then it
base.
recognizes that something is done. So right now,
Small hub cover and casing base
sees that
found.
small hub cover is being put on the casing base, and now
Put
it's
the
done.
other small hub cover.
Small hub cover found.
Unload
So by
the
going
finished
through
casing
this
base.
process, the system is able to build a
Casing
higher
base
level
found.
task hierarchy of this particular scenario, and later on be able to execute by itself or in collaboration with another agent.
Found.
Load
So this is a third use case, which is slightly different from the first two, where the robot is assisting a novice worker. So after it learns from demonstration or somebody programmed it manually, and the system is able to use that knowledge to help and guide a beginner.
Let's start. Put the casing base on pallet.
Is this the casing base?
Look at the side. It is the one with holes.
So in this video, we have these fancy embellishments where the system is talking about
Next, put casing base in upright
automatically
position
talking
and
about some
insert the breather plug
characteristics
into
of
the
these
hole on
objects,
top.
But those are just fancy things we added in to get nice video.
Next,
But
insert
basically,
two oil level
the
indicators
system
on the side
guides
holes.
the user to go through a process. You see this test decomposition on the left, and the system tracks what kind of subtests are being
Flip the
done
casing
right
base
now.
and get the output
And it
hub
talks
cover.
about things the user needs to be careful about. And also sometimes the
Okay,
user
put the small
will
hub
make
covers.
mistakes, and the system will detect that something is wrong.
No, you chose the wrong object. Replace input hub cover with small hub cover. Next, secure the hub covers
And once
using
it
hub
detects
cover
something
bolts.
is wrong, then it's gonna interject and try to tell the user to fix it. And this way it keeps on
Casing base
going
assembly completed.
and guiding the procedure
Now, please assemble the casing top. Put the output hub cover on the casing top. Then put the input hub cover and small hub cover. Careful, the input hub cover should be on your right.
And you can also think about the user's viewpoint where it says
now screw all the hub
needs to
cover
go
bolts.
to your right, your left, or something like that. So you can take a very primitive model
Casing
of the
top
human
assembly
and try to explain
completed.
it in the human's perspective.
Next, install the input sub-assembly in the casing base.
Which one is the input sub-assembly?
The one on the furthest left, with a thin shaft.
And notice that there are these interactions between the user and the system that where the user asks something and the system answers it.
Wait, the input sub-assembly should be on the left. Yes, it's correct now.
So basically
next,
this video
transfer sub-assembly. Then, output sub-assembly.
Instructions back to the user and the action tracking in the world, and also some interaction to do question answering. Okay, I'm just going to stop it there. So, in summary, we know human-machine collaboration is useful in many domains, and we need to enable machines to adapt to humans and human work environments, rather than humans adapt to the robot environment and try to work with them in a very awkward way. And we take an integrative approach to collaborative intelligence and extend a cognitive architecture to allow multimodal perception and inference, intention recognition, plan understanding, common sense-based language understanding, and learning from instructions and observations. So like I said, this project is only past the first year, and it will happen all the way up to year 5. So I hope we'll be able to report a lot more on this in the near future. Thank you very much for your attention.
Thank you very much, Dongkyu. And we still have about 6 minutes left for some questions, and there's several questions posted on the chat. I'll ask them one at a time. I think I'm going to go in reverse order. Stephen asks, could you describe in more detail how the segmentation mechanism delineates actions?
So I guess Stephen is talking about the event segmentation mechanism here.
Yes.
So for now, we have fairly basic segmentation mechanism where the system just looks at what kind of actions are being executed. So we assume that this system is able to detect the low-level actions from the video feed. So once the action changes, that's a potential event boundary. Not always true, but most of the times. At least it works for now. But later on, we're going to have more sophisticated episodic tracking system. Like right now, we have an episodic memory system that can store these events as it happens, and the event segmentation is fairly limited. But later on, if you have a better segmentation, like event segmentation theory, like system, then we'll be able to detect them in a more robust way. But for now, we're just using the low-level actions to detect the boundaries.
Okay, thank you. Greg asks, what does using a cognitive architecture add in terms of insights or functionality or teamwork beyond what other similar projects have done? Andrea Tomas has some similar examples and systems. So
when I say I'm using an integrative approach, so the very first characteristic of that is not just adding a new module for new functionality, right? So I want to use the existing system structure and try to come up with a process that can basically embody whatever phenomenon you want to model. So that's the idea. And let's see. And I believe that's more plausible because it's more human-like, I think. I mean, we don't add new components for a new function whenever we learn to do these things. So I think it makes more sense.
Okay, good. John asked, are there ever any ambiguities between human actions, environmental dynamics, and the agent's actions and their entailments, making it difficult to identify human action?
Okay. So right now, we're mostly ignoring these ambiguities, right? So we assume that we can detect human actions fairly well. But we also, when things get more complicated, we also have these supplemental information like human gesture, like pointing gesture, and the proximity of an object to a human hand and things like that, so that we can decide whether or not this event occurred by a human or some environmental force like a wind or gravity or something like that. So I'll say we are aware of these potential problems, but right now we're focusing on simpler cases where we can easily detect the human action.
Good.
And
okay.
Distinguish them from other environmental aspects.
Okay, thank you. Question I had, you showed language parsing as an input to the perceptual buffer. And how can such a parser ground the semantics to other knowledge of the agent?
So when I say parsing is happening before the utterance comes to the perceptual buffer, we are currently using syntactic parsing that just gives you different candidates of parse results that comes to the perceptual buffer, and we use the semantic information to decide which one is the best interpretation. So right now, that parsing before the perceptual buffer doesn't really use the semantic information, but after that, we do use semantic information within the architecture.
Okay, I think we have time for one more question before we go on to the next speaker. How do you determine the efficacy of the instructions to the humans?
Well, that's a good question. So right now, the system just assumes that these instructions are fairly complete and it has all the necessary information for the task. We haven't really thought too much about this aspect just yet.
Okay.
Yeah, I'll just stop there. Yes.
There are a couple more things on the chat that you can answer, but we're out of time. Thank you very much,